Share screen. Start. Down. We are MA80. This is our 20th lecture. MA080 lecture 20. Alright, and this is graphing containment. Pencil go. So again, as a reference, we are in the algebra textbook. And we're in chapter 4. And right now this is like section, not 6, but 5, and what we will get to is 7. So 5 is what we're reviewing right now, and 7 will be the new stuff. But the last class section, I started it, but I wasn't able to finish it because there's a lot of questions in terms of going on. So we'll see how quickly the 8 of you go. So if you watched the last video, right, which was lecture 19, right, we talked about, or I discussed about, slope properties, right? So remember, we were discussing slope properties. And then if you happen to remember, that's fine. If not, I'm going to write them down really quick right here. It's when the slope is greater than 1 and when the slope is less than -1. That's one of them. There's another when the slope is between -1 and +1. So the first one, it's when the slope is bigger than just 1 in general. And then as well as less than -1. And then you can see that the second property here, it's when m is strictly between 1 and -1. And then you just have to also worry about when they stand alone by themselves, when m is positive versus when m is negative. M is less than 0, right? So the first example we have is, say, look at this one. And hopefully via the videos, you've watched them, or at least you familiarize yourself with them. Because remember, this is all a review, right? You've all seen this at one point or another in your academic career. Whether you enjoyed it or not is a different story. However, aside the point, you've seen it before. You've been exposed to it before. So you have y equals 3x minus 2. And then I'm going to draw this graph really quick. I'll keep the properties of slope right there so you can keep it as a visual. And I'm going to draw this really quick. Y, x, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So if you remember the last technique I did with slope-intercept form, that's the, I like to describe it as the best way of graphing, but it may not be the best for everyone. However, I think it's one of the easiest. So you start with the y-intercept, which is -2. So on the y-axis, you go down to 2. And the slope here, remember, is not just 3x, it's only the number 3. So when somebody says, hey, what's the slope of this graph? It's always the number, again, in front of the x, not the x itself. So m is equal to 3 in this case, more specifically 3 over 1. And then what do? You graph it, right? This tells you to rise 3, and then you're going to run right, because this is a positive slope right here, right? This is a positive number. So in other words, you go up 3 units, 1, 2, and 3, and then you're going to run to the right 1 unit. And then when you graph this, lo and behold, it's just this, right? Now let's discuss the properties that I mentioned before, though. You may have seen it where I talked about positive and negative slopes, and you might go, well, what do you mean by that? We'll take for a moment, consider just the x values. Consider the x values. If you're looking at a coordinate plane, right, the right side here, these are the positive values. And then on the left side here, these are the negative values. So what do you notice about this slope? This slope of 3 over 1, right? This is greater than 1. So that's the third bullet here. Right? It's positive slope. So it's this one. And it's also this one. So this one had to do with positive because it had to do with the direction of the slope. So if you follow from bottom to top of this graph, notice how it's going up and to the right. See, positive. If it was negative, it'd be going up and to the left, which it isn't. See how the orange line doesn't veer anywhere to the left? Now you might argue that, oh wait, but the line is going down and to the left. But that doesn't matter because to say down to the left and up to the right, they're equivalent. So people always focus when they're teaching this to say, oh, notice the top of the graph. Which direction is it pointing? It's pointing in, as you can see, my squiggly pink line. It's going up to the right. So it's positive. That's the direction. And then the first bullet here, this talks about shallow versus steepness. Versus steep. So in fact, I should erase this. This is steep. The first 2 bullets talk about shallow versus steep. So versus. So here, we're talking about how the graph looks, right? If it's very steep, as you can see this this orange line, it's going up pretty fast, pretty high, pretty fast, right? It's not like something shallow, like think of a shallow pool where it's like really low key, like that line that I'm going to erase right now. So this is an example of where this is a positive direction slope, aka my graph is moving up and to the right, and it's also a very steep line. Why? Because my slope is greater than 1. Okay? Positive slope, and it's greater than 1. How do I know it's positive? Again, the number in front of the x is 3. It's a positive 3. How do I know it's heading in the positive direction? Well, the top of the graph, it's on the right-hand side of this coordinate plane. So that's it in a nutshell. Those 4 properties I last discussed about. Now, if I give you another example, right? Nothing too crazy. But I'm going to keep this image here. So these were the properties. I didn't find nothing. These are the properties. Here's the image of first example. Now if you do example 2, which I'm going to change up a little bit here. So here's example 2. And you have y equals a negative 1/2 x plus 1. If I draw this graph, draw on the right side here now. There's your coordinate plane. And then you're going to do the same thing, right? Start with positive 1 as a y-intercept this time. And you can see that the slope, hopefully, is clearly different by being not only 1/2, but it's a negative 1/2. So it's negative this time. However, the technique is still the same. You rise up 1, and you're going to run 2, but this time to the left because the slope is negative. So you rise 1, and you're going to run to the left, not 1, but 2 units. So your point is right here. And then now when I connect these 2 points in a line, oops, that's a little off, sorry. There you go. That's good. See? And you can do the same properties, right? This is the bottom of the graph. This is the top. When you go from bottom to top, which direction is it going? Well, it's going up and to the left. And remember, a negative slope always goes up to the left. A positive slope goes up to the right. Now, why do you want to keep these in mind? Well, when you see a problem on the final that asks you to describe the direction or try to figure out which graph is the correct answer with the algebra equation without having to do a whole bunch of math, this is supposed to help you with that. It's to help you streamline the process so you can identify a lot faster without having to do a bunch of work. Okay, so you can see that this one is a negative slope, so it's less than 1. Negative 1/2 is less than 1, so it's a negative slope. But you also notice it's a very shallow slope, right? This number of m, not only is it m equals negative 1/2, negative 1/2 is between negative 1 and positive 1. So you know it's going to be a very shallow slope. So that's why you can see it doesn't spike up at any point. It's just a slow, steady growing graph. Now, it might look like a spike from your perspective because I'm drawing it zoomed in and the lines are obnoxiously long. Yet, that's why, right? That's why it's the way it is, right? It's heading in the negative direction because the slope is negative, and it's a very shallow one between negative 1 and 1. Now, someone may ask, well, why is 1 special? What is so special about 1? The reason is that, so before I scroll down further, what questions do we have here, if any? Because after this, I'm going to explain why 1, and I have to scroll past this because I have to draw another image. Okay, so let's show you 1, or how come 1, I should say. So example 3, people should see this before, but say you had the equation y equals x. Very fundamental, right? It's nothing difficult, it's nothing fancy, and yet it's necessary to understand from the bigger scheme of things as to why people can say, oh, why is it that you can say the negative 1 is saying positive or negative, or why do you know that's always going to be steep or shallow? Things like that, right? Why can I make these blanket statements? Well, what does this graph look like? Well, this is generally the first graph that most people are introduced to because it's very simple to construct. Even if I don't draw something very big right here, and I just make, let's say, 3 tick marks. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Well, if you graph x equals 1, you get y equals 1. If you get, well, x equals 2, y goes up to 2. If you graph x equals negative 3, it goes down to negative 3. So you can see it splits the coordinate plane right in half in the diagonal. I know I'm not drawing it exactly to scale, but let me draw my blue dot a little bit higher so I can cheat. Yeah, there we go. Something like that. And the purple dot is about right there. All right. So there you go. There's your graph, y equals x. What makes this so special? Well, if you didn't know, if you notice every time I drew the coordinate plane, I always drew it in a cross. And so when you draw in a perfect cross like this, I can also draw this little box. Anybody remember from geometry, what does it mean when you draw a little box like that? What does that mean about the coordinate axes, x and y?
It's a right angle.
Right angle.
Right, it's a right angle, right? Wait, did everyone say right angle? Or did someone say something? I thought I heard something different. No? Everyone said right angle? I heard three voices, sorry, that's why. So it's right angle, right? So that means each of these are right angle. And if this orange line splits the right angle in half, that means, don't worry, I'm not going to ask you too much about this part. This part's not going to be final, but it's important to know. It means that this portion is a 45-degree angle. So that's why the number 1, is important in terms of our visual here. Because algebraically, you all know already that the slope here is 1, or more specifically 1 over 1, right? If you move up 1, you move to the right 1. If you move up 1, you move to the right 1. If you move down 1, you move to the left 1. If you move down, very easy to construct. But what happens when you have a line that goes up through the middle, through the origin, right? Like this. Right? What is this slope? I don't know, I just made it up. However, since you see that it is quite steep, you know that whatever this slope is, you know that this slope is greater than 1. Okay? Because 1 gives you that benchmark of being in the middle, if you will, right? Half of 90, 45-degree angle splits the 90-degree angle in half. So you know that whatever this angle is, again, I know we're not doing geometry here. Wrong color. You know that whatever this angle is, this angle is greater than 45 degrees. Okay? Now what about the other way around? Let's use navy. What if I drew a line that was very shallow? Maybe something like this. All right? So you can see it's very shallow, not steep at all. So whatever that slope is, hell, I don't know what it is. But what I can tell you is that this slope in navy, it's definitely less than 1. Well, why? Because visually, the blue dotted line is underneath the orange line. Which also means that geometrically, it means that this angle, whatever the hell it is less than 45 degrees. Draw this black arrow a little bit smaller so that I can fit less than 45 degrees, right? So if I zoom in, you can see obviously a little bit better, but you can see that this orange line kind of dictates the benchmark or the middle or the neutral zone, whatever you want to call it, right? And then what about the other half, like all the negative stuff down here that I didn't draw? Well, that's the nice thing about geometry to some extent. It's that it's all a mirror. So this bubble right here that I'm drawing, this is all equivalent to the bottom side here. Right? It's just a mirror of each other, just backwards, if you will. Well, maybe not exactly backwards, but it's mirrored, as you can see. That's why when I scroll back up here really quick, you can see that steep applies to slopes that are greater than 1 and less than -1 because they have the same properties when you're looking at either side of the graph. And same with shallow, same with the positive direction, same with the negative direction. So this is it in action when you just look at one graph at a time. But when you're looking at multiple graphs at a time, then you kind of see, okay, orange or y equals x, my benchmark of a slope of 1. And then now I can kind of see when something goes way super steep. That's because, again, the slope is greater than 1. Or something that goes super shallow, and that's because the slope is less than 1, right? So that was a quick review of whatever the last lecture was. I think it was lecture 19 or something. And just going over those properties because they're going to help with this next concept, which is the last one of this section, I believe 5, I said. So before I move on, what questions do we have on these properties, if you will? All right. Okay. Feeling okay? So that's that, right? But then you find out that from the slope, we can actually address when you have multiple graphs or multiple lines in a single coordinate plane. Let me write that out for you. Actually, I'll write it here on the side, save some space. From slope, or from understanding slope. Oops, that's not how you spell standing. We can address and maybe even identify multiple equations or multiple lines in a single coordinate plane. If you notice from homework, or even practice or lecture or a combination of it, every graph was plotted on a single coordinate plane, right? Example 1, one graph. Example 2, one graph. Example 3 here was the first time you've seen anything in multiple. And I'm not saying first time ever in your life, just as far as this class is concerned. So you're going, okay, we're going to look at multiple things now. Well, consider graphing this. This is example 4 here now. So there's that. So now example 4 is going to say this. Graph both equations technically on the same plane. But you already know you're going to do that. It wasn't obvious, right? So you have y equals negative 2x plus 3 and 2x plus y equals negative 1. So I'm going to scroll up now. Plot these. Draw these axes really quick. Give you a moment to catch up. That should be fine, right? Yeah, that should be good. So what do you do, right? Well, you do a lot, or very little, depending on your preferred method of graphing. But I'm going to put them in slope-intercept form, as per usual, and then we can adjust the graphs together. So the first equation, hopefully people will recognize that it's already in slope-intercept form. If you look at it, it says, oops, that's not supposed to go there. Toss this over here. The first graph, it says y equals negative 2x plus 3. So in purple, or just a different color, I should say, you have y equals mx plus b. It's already in the correct form that it needs to be. In fact, we can graph that first. So you go to 3, and y3 again, because the y-intercept is 3. And then our graph has a slope of not negative 2x, but just negative 2. Remember, it's just a number in front of x, and it's over 1. Remember, any integer that you see without a denominator, it's technically over 1. And you're going to go up 2 units, and you're going to move to the left 1 because it is negative. So I'm going to do my best to draw this. Wait. There you go. So here, no, that's not good. Okay, I think that's the best I can do right there. And there's your purple line, right? Then when you look at the second one, which I'm going to do in navy, you need to get y by itself. Well, this is one of the easier ones, right? You just need to subtract 2x from both sides of the equal sign. So you do that, and then this provides you with the equation y equals negative 2x minus 1. And you do the same thing, right? This negative 1 is your starting point on the y-intercept. So you start at negative 1. Hopefully you notice that, hey, look, the slope is the same. Very similar, right? Negative 2 over 1. So you rise 2, 1, 2, and then you're going to go to the left once because it's negative. Draw your little point there. And then you draw your graph. And then you'll find out that I did better this time around. When I did this in my last section, it was pretty awful. And it's still pretty bad here. So it's not exactly, but what do the lines appear to almost be, thanks to my awful drawing?
Parallel.
Right, they're supposed to be parallel lines. You know what, I'm going to try one more time. This is pretty bad. They're supposed to be, nope, that's not it. They're supposed to be parallel lines. And when you look at both equations, what's the distinguishing factor that you can point out to make you feel like, this is in fact parallel? What do both of these equations share in common? So yes, parallel lines.
We have the same slope.
Yeah, they have the same slope. So if you remember that from your algebra days, it's because they have the same slope. See, it's this right here and this right here. It allows you to go, oh yeah, same slope. Same slope implies parallel lines. And in fact, not that you need to see like a whole bunch of examples on that, you know what to pinpoint in terms of the slopes, I can give you a little bit of a definition right here. And it's that given 2 or more, for this class, all intents and purposes, you're more than likely going to see only 2 at most. But this technically applies for more, right? 2 or more linear equations if they share the same slope then the 2 or more lines are parallel. Now underline that in purple because that's technically a definition or a terminology you should at least recall from, if not algebra, definitely your geometry days. Because they talk about it both. Algebra shows you the algebraic form, like I did right now with the whole idea and the philosophy of the same slope. Geometry shows you the visual sake or the visual acuity of why they're parallel, right? And I'm sure you've heard this time to time again. It's the same example that every freaking teacher uses, but right, parallel lines are like train tracks, right? Train tracks never cross. So whether you're in the MTA, in the subway, or the Long Island Railroad, or the Metro North, right? You notice the tracks, they never cross. If they cross, the train derails, and then we got a big accident on our hands, right? But that's the philosophy of parallel lines, right? They never cross. There's never an intersection with them. And now, the beauty of understanding this in terms of the slope is that if I give you 2 equations, you can tell me right from the get-go by just manipulating the equation into slope-intercept form of whether they're parallel or not. And you don't have to graph squat. You have to graph nothing, right? You can determine just by checking out the slope. And that's supposed to give you the foresight of doing it quicker, essentially, without graphing. But what if I give you these 2 graphs to graph? So everyone, is it okay if I move on to the next example? I know, you know what? Let me leave that right there, just in case if people are still writing. So again, this was an example of parallel lines. There's a statement in green that I left it. So now I'm going to say graph these 2 lines instead. Graph the following. That is not how you spell follow. So now I'm giving you y equals, well, the textbook actually. Y 1/4 x equals, minus 1 and y equals negative 4x plus 2. So this one's nice because they already gave it to you in slope-intercept form. You don't have to do much manipulation there. Is it okay I scroll down from the, well, better yet, is anyone still writing the green text about parallel lines? Okay, I'm going to take that as a no. So let me draw this graph now. Here's a coordinate plane. Again, same philosophy, y. X. Let me draw my little tick marks. And same thing, I'm going to start with the one on the left. So there's our purple line. And you start at -1. And you can see that the slope is already 1/4. M equals 1/4. So you can ask yourself the same thing, right? You know it's going to be a positive line. It's going to go up and towards the right, but you know that it's less than 1, so it's going to be very shallow. So you move up 1. So now I'm on the x-axis, and then I'm going to move over 4 units, 1, 2, 3, 4. So you know that the point I'm looking for is there. Oop, nope, that's not good. That's not good either. Come on. No, that's almost. There we go. This should be good. So if you recall, right, from the beginning of class, this is the top, even though it's a very small top. This is a bottom. Again, a very shallow line. However, it's still moving up and to the right on the positive direction that way. I'm not going to keep that there, but it's just to visually show you. All right. Now, as for the other line in navy here, starting at +2, and then we're actually going to rise, even though it's a -4/1, we're going to rise 4, and then we're going to run to the left because it's negative, and we're going to run 1 unit because, well, it's over 1. So 1, 2, 3, 4. You're going to move to the left once. There's my point. And I'm going to try to draw this one. Almost. A little bit steeper. Too steep. There we go. That should be good. So same philosophy, right? You can see that this one is the bottom of the graph. This is the top. But now you can see it's super steep. Why is that? Well, the slope is -4. And some of you might go, oh, but that's smaller than 1, right? It's not greater than 1, it's smaller than 1. But not only is it smaller than 1, it's smaller than -1. It's going in the negative direction, right? So remember, positive on this side, it's going up on this side to the left, so it's negative in this direction, right? And that, again, that's just pulling in the ideas from beginning of class. Now, my question to you, to everyone, is that when you look at this intersection right here, what does this intersection remind you of? Or what does it look like? And what would you tell me? Or what would you think to tell me? Or maybe it doesn't look like anything, and that's okay. But I need to get an idea of what you are thinking, if anything.
Is the intersection the solution?
Yep, this intersection is the solution. If I were to ask you to say, hey, graph these 2 lines and give me the solution. So, sorry, who was that was asking? I mean, giving that answer?
Oh, it's Maria.
Maria. So if you're like Maria and you're like, oh, I remember this, when you graph two lines, that's the solution of the graph. It's the point that they both meet at. So if you're like Maria, you're actually ahead of the game. You're jumping ahead of me for the next chapter, which is great, right? So this is definitely an intersection. It's a solution, right? So then my follow-up question to that, because that is a correct response. I guess, you know what? I probably should have said instead the same thing I said last class. What does this look like? So that's my follow-up question. What does this intersection look like? So now I'm asking you for a geometrical perspective. Intersection look like? So what does this solution look similar to when you look at it? Would you say it's fair for me to draw this little symbol right there? Would I get arguments of people going, you don't know that? Or people saying, it kind of looks like it. Kind of looks like the origin of a graph, right? I mean, of a coordinate plane. Agreement, disagreement, not sure.
Agree.
Agree. Okay. That's 1 out of 8. Well,
Okay.
it turns. Sorry, I interrupted you. Go ahead.
No, I just said agree.
Okay. So I'm sure people are getting the idea of how I'm supposed to. I'm sorry, not how I'm supposed to. People are getting the idea that I'm scaffolding you to talk about the next thing, right? So we have parallel lines, and now if you remember from, again, geometry, we have what are called perpendicular lines, right? And what I'm trying to tell you or show you or convey or whatever you want to call it is that, in fact, these lines are perpendicular. And how do you know that? Well, just like the same way where, I forgot who it was. I actually didn't ask, I think. But whoever it was that said, oh, the parallel lines, they have, or maybe it was Maria, I forgot. But the parallel lines, they have the same slope, right? Well, here in this case, they don't have the same slope, but they have something unique to one another. So let me write down what I'm trying to convey now. Now you're going to get this in words, right? So this is the answer, if you will. And then now I want to say exactly what I defined. So two lines that intersect and form or create, however you want to think of it, a 90-degree angle are called perpendicular lines. Perpendicular lines. Just as a heads up, if anyone was curious, the symbol for perpendicular lines in geometry is like that. It's an upside down T. Now, how do we, just like parallel lines, how do you know for a fact, without a doubt, that you have parallel lines without having to graph them? Same question goes here. How do you know you got two lines that are perpendicular without graphing them? Well, it goes like this. Draw my line. Go back to green. Given two linear equations, if their slopes are negative reciprocals then the lines are perpendicular. Perpendicular. And the term here that you may or may not have seen or don't recall, or maybe it's been a while, is the whole connotation or concept of negative reciprocals. So for example, e.g., if I came over here and I said, what's today's date? Today's the 16th, for example, right? We're in, what are we in? November. So say November 16th, 11 over 16. And I asked for the negative reciprocal of it. What do you think that might entail? Now, if you already know the answer, you can blurt it out. But if you don't, then you can, if you don't know the answer, then you can answer this, the question that I just asked, right? When you hear negative reciprocal, what do you think it entails when I give you the number 11 over 16?
Negative 16 over 11.
Hey, look at that. And then how did you get that? Well, I'm guessing you took the exact words and you took it as they are, right? So if everyone remembers, right, the reciprocal of any fraction is when you flip it around, aka you take the reciprocal of it. There's no other way to say it. The word reciprocal is the only word that comes to mind. You could sure say flip the fraction and flip off the fraction, whatever you want to call it. But there's really no other way to say it mathematically. It's taking the reciprocal. And then since I'm asking for the negative reciprocal, that means that since we start with a positive 11/16, we have now a negative 16 over 11. But what if I go further and I give you something starting with a negative number? So say negative 2 over 3. What would the negative reciprocal be of this?
3 over 2.
So that is also correct. Now, if you were like my previous section, you might have asked but didn't want to say out loud, well, damn, the number is already negative. What do I do? Well, it actually doesn't matter, right? The negative aspect of it, to say negative reciprocal, still applies. So the first example, 11 over 16, it was positive. So you take the reciprocal, you make it negative. For negative 2/3, you take the reciprocal, 3 over 2, and you apply a negative to the negative. Well, what's negative times a negative? It's positive, right? Take the opposite sign of it, and then that's it. So that's perfect. That's beautiful. So now you have a tool to say where if I give you two equations, right, you can tell me immediately whether they are parallel, they are perpendicular, or they are neither, right? And it's observation on strictly the slope, all right? And that's the last thing about like slope properties that we have to talk about, because the ones I outlined from last lecture last week, these are minute. They're helpful to know. They help you in terms of scheming and thinking about how to graph it without actually graphing it. But when you know these things, right, about the parallel and the perpendicular, this is great because all you have to do is just manipulate a little bit of algebra and you don't have to graph squat, right? You don't have to do anything. And yet you can tell me whether they're perpendicular, parallel, or neither. Just another thing, parallel lines in terms of the symbol, it looks like an 11, but it's basically just two long lines like this. Oops, not like that. Yep, there you go. So that's parallel. They look like train tracks, basically. So perpendicular, parallel, and that's that. All right, beautiful. So that's section 4.5, right? At the beginning of the class, I said that's what we're wrapping up. So now the inequality part, the last section, 4.7, this is where I almost ended with the previous class. So last section here. Before I move on, what questions about finding the negative reciprocal? There's not real math involved with this, right? It's more like identification more than anything. Sorry, it is real math. It's just that there's no real calculating math, I should say. That's probably the better way of saying it. Right? Cool. All right, so what we can do is we can say, wait, what's going on here? What we can say is, what do we do when we have inequalities, right? That's the thing that we're always looking at to move towards, because first you work with equal signs and then you do inequalities. And then it's always going back and forth, right? Equal sign, inequality, equal sign, inequality. How do we go about it? Blah, 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 this and that. So that leads us to our last section for this chapter. What is it? Chapter 4, I said. And again, we're in the algebra textbook, right? Excuse me. I'll start with a new page here. So last section. No, I'll break the page. Yeah, here we go. So last section. Which is 4.7. We're skipping 4.6 because that part is not emphasized in the course or the final for whatever reason of chapter 4 in algebra text. Now, if you recall, this one we did lecture together at one point. We talked about inequalities, right? We had greater than, less than, greater than or equal, less than or equal. Right? Greater. I'm going to abbreviate this. Greater than, less than, greater than or equal, less than or equal to. I should put that in parentheses, right? Because it's either. It could be less than or equal or greater than or equal. And what I wanted to point out was that of these 4 symbols, right, or 4 inequalities, any of these inequalities can replace the equal sign in slope-intercept form. In other words, when you move from y equals mx plus b, as we learned, right, you can easily go y is less than or equal to mx plus b. But how does that affect the equation, right? Well, it does and it doesn't. Algebraically, when you manipulate or solve for y or move things from left to right of the inequality, it's the same. The only thing you have to watch out for is, remember, when you divide or multiply by a negative sign, you have to change the direction of the inequality, right? I don't mean change like greater than and then all of a sudden change to greater than or equal. I mean just flip the direction, right? If it's facing one way, you face it the other way. All right? But then when you graph it, though, that's the part where it gets a little hazy because there's extra little properties that you have to keep in mind. So before we graph on an actual coordinate plane, let's take a step back and graph on a number line. So if you had this example, and this was in our textbooks, but there's no point of teaching you when it first came up because you don't see where it all ties together. But when I do it here, you can see the relevance, if you will. So for example, I asked you to graph on a number line. So notice how I said on a number line, just not graph, but graph on a number line. Number line. X is greater than 2. You draw your little number line. Start with 0 in the middle. Probably go out 1, probably 2, probably go out -1 as well. So you know you have to start at 2, and you have to put a circle there. But then you would ask yourself, oh, do I put an open circle or a closed circle? Anybody remember?
A closed circle. Wait, oh, if it's later, if it's not greater than or equal to, it's open, right?
If it's not greater than or equal to, yes. So basically, when the inequality doesn't have the equal sign, it's an open circle. And then you just follow the direction it tells you. It wants you all the x values more than, whoops, iPad's about to die, more than 2. If the iPad dies and it just cuts off abruptly, I apologize in advance. Obviously, that means class is over. But we are almost done, though. Let me see if I can get a charger to reach over here. Hey, look at that. I don't know how long this will sustain, though, because using WebEx and something that's very graphical heavy, it might still drain it quickly. In any event, so yeah, open circle, all the values greater than, what is that, 2, I said? So that means you draw the darkened arrow and you move to the right. So I'm going to scroll up just a touch. So that's right. You remember that, oh, with any inequality without the equal, it's an open circle. And then any inequality with the equal sign, it's a filled circle or closed. And the nice thing about this was that when you learned about this the first time, it was easy, right? You looked for a certain symbol. You said, hey, is that open? Is that closed? Is it whatever? And you just copied it and you moved forward, right? You followed the rules and you produced. You gave the answer as you needed to. And there was not much hustle or bustle or argument or whatever you want to call it. And you just did as you were instructed because there was nothing more to, how should I say, there was no more detail outlining what it really meant, if that makes any sense at all. So what do you have to do about that, right? Why do you have to worry about it? Why is it of any concern? Well, it turns out that in addition to the whole open circle, closed circle, and whatnot, I even draw right there, open, and here's filled. Open circle, filled circle. Right? Is that if you take a moment to go further, you actually, what you're talking about is when it's open circle, you are excluding nope, that is not how you spell it, excluding. And then if you are filled circle, you are including. All right. So let's go to an example. But in the back of your mind, for now, at least until Wednesday, actually maybe even after Wednesday, because we'll be lecturing, but you're probably still focusing on the midterm, so that's understandable. But in the back of your minds, right, in addition to greater than, equal, open circle drawn, add to your list of things as excluding. Whereas if you see the inequalities with the equal sign, then you know it's a filled circle or what's the other word people use? Closed circle. Remember that it is including, it is inclusive of the situation. You might go, well, what kind of situation? Well, I'm talking about graphing. Now we're talking about graphing on a coordinate plane, right? So let's do an example. We have, for example, 6. I think this is our last one. Yeah. Graph and shade. Y is greater than 2x minus 1. All right. So that's our inequality now, as opposed to equation. And what else? How do you graph it? Well, you can go about it in any of the 3 ways that we've discussed, which are plot points, use the intercepts, or use y equals mx plus b. But when I did this, I took the time to draw out a graph or a chart so that it'd be more visual for students, for my last class at least. So let me do that for the same here. So you have your x coordinate, your y coordinates, and you pick a couple of points. So I'll choose an easy one first. I'll choose 0. Plug in 0 for x. Outside comes, what is it, -1. Someone give me another number. Pick a number random.
Two.
Sure, let's do 2. So in Navy now, we got 2. So 2 times 2 is 4 for x. Then you guys subtract 1. So you're left with 3. And then I'll just pick another random number. I'll choose -1. Let's use dark green. So -1. -1 times 2 is -2. And then now you have -3. So let's graph these 3 points and see what happens. Wait, is that where I want to graph it? Yeah, that's fine. Right, let me draw my little tick marks. And let's graph these. I got 0, -1. I have 2, +3. And then -1, -3. What the heck? There we go. Let's draw this graph. Now, if for some of you that remember how to graph inequalities, if you remember, great. If you don't, that's okay too. We're going to learn. But I'm going to tell you this is only a partial answer, right? If you gave me this in an open-ended question or in an open-ended exam, you get half credit. Actually, no, you get more than half. You get like maybe 80% or something like that, right? But it's not 100%. And why? It's this whole shading aspect, right? And I'll tell you right now, if you don't happen to remember how to shade, the answer that will be complete is if you shade on this side of the graph, the left side. And some of you might go, well, how did you do that? How did you know that was the answer? Well, there were 2 ways that I learned this. And the first way I learned was very mechanical. It was very algebraic, very rote, if you will. And that's what I learned in high school. And ever since I learned that, I thought it made the most sense. It made sense because I understood it, but it made sense in the sense that It was what I was taught. I was told to learn it, and I just learned it, and I repeated it, and I recreated this situation whenever I was asked to, and that was it. When I was teaching algebra as a teacher this time in high school algebra, I told my master teacher, like, oh yeah, this is how I learned it. But as I'm sure if you all know, just because you learned one way does not mean it's the best way to teach. And of course, as you can imagine, my master teacher said, hell no, you can't teach it like that. They're not going to understand squat about it. And then my master teacher gave me another visual in terms of how to go about it. So I'm going to show you both, right? And then you pretty much pick whatever method you like the most. But so there's no ambiguity, which I want to make sure I state this first, is that your answer must be inclusive of all of this, right? Answer includes graph and shading, right? You can't leave out one or the other. It needs both. And that's the purpose of graphing inequality, that is. Okay, so how do we do this, right? Well, there's a couple things to keep in mind. So first and foremost, the answer must include the, what do you call it? The graph and the shading. But there's also one extra thing you have to worry about. And it's the fact that, let me write this in green, light green, it's this inequality. So here comes one of the first of a couple of rules to remember. When an inequality has equal the graph is a solid line. So that's what we have here. If or I guess I could say otherwise, the inequality has a dotted line. So what this means is that if you ever run into an inequality and you're graphing it, right, and you see the equal sign, doesn't matter which direction you're spacing, when you graph it, you better graph it as a solid line like I did for this example right here. Otherwise, in case you were wondering, in other words, if you have an inequality and there isn't an equal sign, when you graph the line, you got to graph it dotted. Like I mean, obviously this example doesn't have it, but that's why I wrote dotted line and I used dashes on the bottom instead of another solid line. So nice little pun there to keep you in, not in check, but just to remind you. So that part's relatively simple because you graph the same exact way. You just got to remember, oh, is it solid or dotted? Is it solid or dotted? Do I have an inequality with an equal sign or do I not? And that's pretty much it. The shading, however, that's the part that I feel students generally miss, right? Do they always miss it? No, of course not, because there are students that know how to study, test, perform, and all that, all those adjectives, if you will, describing students. Maybe verbs. To study? No, it's verbs, right? So how do we go about the shading? Well, I have it in 3 steps. And this is, by the way, the mechanical way of going about it. In other words, the way I learned it when I was in high school. Okay. I gotta pick up this iPad. All right. So how to shade. Let's scroll down here. So step 1, you want to pick a point not on the graph. So say we didn't have the shading right there, right? And you graphed just to this point. And you're like, hey, I feel confident. Got these points correct. Graphed my graph correctly. Now I just got to shade like Professor told me. Step 1. You want to pick a point not on the graph. So you see those orange, you see that orange line, you see 3 colored points right there. So those 3 colored points, they don't count, right? Because they're on the graph. So what line do you, what point do you see that's not on the line? What's a very obvious one? And if not obvious, someone give me one. On the chart, you can see that if you plug in 0, you get -1, 2, you get a 3, -1, -3. So you can't pick 0, -1, 2, 3, -1, -3. Those are all points that construct your graph. What about a point that isn't on the graph, or basically a point where this orange line won't cross for sure?
4 and 4.
Yeah, 4, 4. What's easier than that, though? I'm going to use 4, 4, but what's in the center of a coordinate plane? Starts with an O.
0, 0.
Yeah, an origin, right? Now, if that graph crossed 0, 0, then you can't use it. But here, 4, 4, I know it's not going to cross that, so that's okay. We'll use that, so that's not a problem. All right, so you pick a point not on the graph. So we did that. Cool. I don't know why my H looks so weird in graph right there. Let me fix that. There we go. So then what's the second step? The second step is to plug in the point to your inequality and check whether it's true or false. So you go pick a point on the graph, plug in your point into the inequality. And check. I wrote the ampersand and, but now I'm getting tired. And check whether true or false. So in this case, remember the equation or the inequality was, again, I'll write it up here again. Y greater than? Yeah, y greater than 2x minus 1. So I'm going to go y. No, I'm going to go 4 greater than 2. Wait, greater than or equal. Greater than 2 times 4 minus 1. So you're left with 4 on the left-hand side. On the right-hand side, we got 2 times 4 is 8. 8 minus 1 is 7. So we ask ourselves, is this true or false? You would say what? Is it true or false that 4 is greater than or equal to 7?
False.
You would say it's false, right? Then comes step 3. So if it is true, I guess I should write it like this. So here's step 3. If true, oops, shade the region where the point lies. If false, shade opposite to the graph. Is that how I said it? What did I say? False, shade the opposite side of the graph. Ah, yes, it is. Okay, so now we look for 4, 4, right? Now I plugged in 4, and we got, what, 7? So you plug in 4, here's 4, and then you go up 7. Got to draw more ticks. 5, 6, 7. So here's 4. I'm going to go up 7. 1, 2, 3, 4, 5, 6, 7. So it looks like it's on the graph, right? But it's not. It's actually a little bit above it. No, I'm sorry. I'm sorry. I said that wrong. So 4, 7. But we picked 4, 4. So that's what I was trying to say. Just kidding. This will be a 4. So our 4, 4 is our checkpoint, right? So we look at 4 and we go 4, 1, 2, 3, 4. So here's 4, 4 right here. So here's the visual for it. There's 4, 4. And we ask ourselves, does 4, 4 lie on the graph? And the answer is no. That's why we picked it. And then we plug in our 4, 4 point and we check to see if it was true in an inequality. And it's false. So what does step 3 say? It says if it's true, you shade the region where the point lies. Well, the point lays on the right side of the graph. Does everyone see that? Right? It lies on this side. So you would shade this region. But the thing is that it wasn't true. It was false. So if it's false, that means you shade not there on the right, but boop, on the left side now. So you shade opposite of wherever that point sits. And that's how you do it every time. Right? Obviously, we're going to have to practice this more because we have to worry about dotted line, solid line, and then this whole shading thing. And I have to show you how to shade that is not this mechanical, right? It requires those that have more of a visual learning method. If you prefer visual, this is probably what you're going to understand more, hopefully, when I show it to you on Wednesday. But beforehand, at least up until this point, what questions do we have here? Or what questions do you have for me that may not make sense and you need me to clarify? So this is as far as I got from my last section, right? And that means that all we have to do is just practice one or two more of this type of problem, right? You now have a solid foundation in terms of how to go about it. I'm going to teach you an alternative way on how to shade. Practice one more problem, and then we'll be done with this chapter. And then obviously that means on Wednesday we'll start chapter 5, get as far as we can on there, and then next Monday, hopefully, we'll even finish chapter 5. That's a big hopefully, though. Okay? In the meantime, what questions do you have for me? Now, shut up and focus. All right, I don't hear anything, so I just uploaded this document, this PDF of the notes that we wrote today. Let me stop sharing now. Oops, that's my thumb. All right, so, oh yeah, I forgot to check the chat if people were writing in here. Oh, the date of the final exam. All right, so the date, wait, let me look at the calendar again. The date of the last lecture is supposed to be, according to the academic calendar at FIT, which I can send it to you in an email as an attachment so you can have the PDF. It's supposed to be December 23rd. But that's the week of Christmas, so I don't know if I'm going to do that. But I wouldn't be opposed to giving you the final on the Monday of that week, depending on how much time people need to study. And so what happens